Hi everyone, welcome back to the Heterogeneous Parallel Programming class. We are at lecture 2.2, kernel-based parallel programming, and we will be focusing on control divergence in this lecture. The objective is to help you to understand the implications of warp scheduling on control flow. And we will first briefly review the nature of control flow in CUDA kernels, and then we will talk about how the warps are partitioned, and then we will discuss the nature of control divergence and the implications of control divergence in CUDA kernels. This is a review slide from the previous lecture. So warps are the scheduling units in CUDA kernel execution, and each thread block is divided into these 32 thread warps. And this is an implementation decision, not part of the CUDA language. Up to this point, all the CUDA hardware that we know of use 32 thread warps. And these warps are scheduling units. Whenever they get to execute in the hardware resource, they execute in the SIMD, or single instruction multiple data manner. And the threads are in the warps are executed. They all either execute or not execute. So in order to understand the nature of control flow, we need to go back a little bit into the von Neumann processor model. So in the von Neumann processor model, remember, we were fetching instructions from the memory. And every instruction needs to be fetched, then executed. And the instruction that come in three flavors. The operate instructions, which means there are arithmetic instructions, logic instructions, and some various data manipulation within the processor. Data transfer, which means there are memory loads and stores. And then there are program control flow. And these are the instructions that will cause control flow in the activities in the processor. So in a typical processor, we will fetch an instruction, we'll decode the instruction, we'll execute the instruction, and it may access memory for its operands. So we now can focus on the control flow operation. A typical control flow instruction would be a branch instruction. And these branch instructions come up because of the control statements in the C or CUDA source language. For example, when we check check whether a thread falls within the valid range or not, that if statement would create one or more of these branch instructions. Another example is loops. So when we talk about the matrix multiplication example, the loop that we have in the kernel, where every thread is going to iterate through the row of A and column of B to do the dot matrix, that loop will have a conditional instruction that will take the control back into the beginning of the loop or exit the loop. So whenever we have these control flow instructions, they will determine which path of the original program will be executing for the processor. So now we understand some of the basics. We can actually go and look at the implications on the execution of warps. Remember that these warps are going to be executing in single instruction multiple data mode. So let's say if we have a branch instruction in the program, and there are 32 of these threads all executing that branch instruction. Let's say if the branch instruction is taken for some of the threads, but not other threads, then we have a problem because the SIMD execution can only execute one instruction. However, after that branch instruction, some of the threads will want to execute one path of the program, and the other instructions will want to execute another path of the program. So we need to understand how this is going to be handled by the hardware. So in CUDA processors, what happens is that all the threads will be executed for one of the paths first. And then only the threads that actually have the branch going into that path will be allowed to take effect. So we will do one pass through all the instructions on that path, and then we will take another path through the other path. And that path, we will only allow the threads whose branch will want to go to that other path to take effect. So this is the reason why whenever we have a situation where some of the threads in a warp want to take one direction in their branch and other threads want to take another direction in their branch, we will have performance loss because it actually takes two passes through each one through these different paths in order to complete the execution of all the threads in a warp. So whenever this happens, we start to lose performance. And how much performance do we lose depends on how the threads, how the warps are executed, and how the branch actually take effect. So if we have a conditional branch in the code, it doesn't mean that we're going to have performance loss, because as long as all the threads take the same direction in a warp, all the threads take the same direction, then we are actually going to have negligible performance impact. What happens is that when we actually have threads that want to go to one direction versus other threads want to go to another direction in the same warp, that's when we have a performance penalty. So that is important to understand a little bit more details about how the warps are actually formed from thread blocks. So whenever we're given a thread block, we're actually going to partition the thread block into warps according to this following rule. We would use the thread ID, and all the thread IDs within the warps are the same warp are consecutive. So consecutive threads in their ID will be formed into the same warp. And we will start warp 0 from thread 0. And you're going to ask me, what happens if I have multi-dimensional thread blocks? In that case, we will do a row major layout of the threads, and then we will apply the same rule to partition the thread block into these warps. And the partitioning in the hardware is always the same. That is, the rule that we use is always the same. However, there's no guarantee that the warp size will remain the same in the future. Even though all the current generation and previous generation CUDA hardware use 32 thread warps, there's no guarantee that we will not have 64 thread warps or 16 thread warps in the future. So we cannot rely on a particular size, and also we need to make sure that we don't always assume that every 32 warps will be threads will be executed as a warp, because in the future they may be broken down into two different warps, and then they may execute in parallel with each other, independently of each other. So now let's go back to the control flow instructions. And whenever we have a real divergence, that is, when we look at the execution of a warp, if some of the threads truly want to take one direction for a branch and other threads want to take the other direction of the branch, that's when we have a real control divergence. That's when we need to have two passes through the different paths of the code in order to execute all the threads. And these different execution paths are serialized in their execution, so their execution will add up in the total execution time and therefore cause our performance penalty. So if we go back into some real examples, if we see a if-then-else statement where the condition depends on thread index, then there is a chance that we may have a control divergence. For example, if we have a test saying that thread idx.x is greater than 2, and this condition separates out the threads in a thread block into two groups. One is thread ID, all the threads with thread index equal to 0, 1, and 2. And the other group is thread index 3, 4, and beyond. So all the threads with thread index less than or equal to 2, and all the threads with thread index greater than 2. So for the first warp of that thread block, we will have control divergence, because the first three threads in the warp will want to go in one direction, and the other 29 threads in that warp will go in the other direction. However, for warps that are of higher thread index in the thread block, those warps will actually all be in the same group, and they will only take one path. And those warps will experience little or no performance loss due to this conditional branch. And obviously, if the branch condition does not depend on thread index, for example, in the bottom here, we have a test of block index greater than 2. All the threads in the same block will have the same condition. So naturally, all the threads in the same warp will also have the same path. So in this case, little or no performance penalty will be experienced by any of the warps in the grid. So now let's go back to our vector addition example. So remember that we have a test here that is testing the I is less than n. So we will have a situation where within the same block we may have a control divergence, but we may not have. So let's go into a little bit more analysis in the next slide here. Let's say if we are processing 1,000 elements in our vector addition. So all the threads in blocks 0, 1, and 2, assuming that we're using 256 threads in a block. So all the threads in blocks 0, 1, and 2 are within the valid range. That means that all the threads in all the warps in those blocks will be taking the then part of that if then else statement. So for all the I values from 0 to 767, there will be no control divergence. On the other hand, block 3, the last block, will experience some control divergence, but not to all the warps. All the warps from 768 to 999 in thread index will actually still go in one direction. They all still fall into the same the valid range. The only real different control divergence actually happens in the very last warp of block 3. And essentially, you will have values from 1,000 to 1,023 that are outside the valid range. So 24 of those threads in the last warp will want to go one path, and the first 8 of the threads of the warp will go in the other direction. So this means that only the last warp out of the numerous warps. In fact, we have 32 of these warps, and only the last warp will actually experience control divergence and the execution of 2 passes. So this means that the performance penalty for the kernel is actually be very minimal, because only a very small percentage of the execution will experience the effect. So this concludes the considerations of control flow, and when control divergence happens, and the consequence of control divergence, and some analysis of our boundary checking code. And hopefully it has become clear that the boundary checking code, even though it will cause some control divergence, it only causes control divergence to one of the warps of the execution, and therefore the real performance effect of the control divergence will be very small for the application. And I'd like to encourage you to read the textbook section 4.3 if you want to learn more about the nature of control flow in CUDA kernels. Thank you.